Today, let's have the lecture about limits and continuity at a point. So as we have observed in our discussion of limits during the midterms, there are functions whose limits are not equal to the function value. That is, at x that is equal to c, that at times when you're going to solve for the limit of the function at that as x approaches c may not necessarily mean that that's equal to f of c. That is why we have the rule limit of f of x as x approaches c is not necessarily the same as f of c. Remember that when we are solving for the limits, there is what we call the function is undefined at a given value of x. However, when you check the left and the right hand limits, then they are approaching the same value, meaning to say the limit does exist. However, when the left and right both increase infinitely or decreases infinitely, then the limit does not exist. However, we indicate that into infinity. Now, because of this definition, we will now have the study of continuity of functions. Now, why do we need to know about the continuity of functions? These finals, we shall be moving to derivatives, and one of the definitions that you really need to understand is the differentiability. So the continuity of functions, we'll talk about differentiability of the functions, and we'll get more of them as we go through. Now, the limits and continuity at the point means that you are going to determine that particular value of x that will let the function undefined. So you're going also to recall the rule of domain. Let's have the first example. We consider the graph of f of x is equal to x squared plus 2x minus 3 over x plus 3. Now, when x is equal to -3, then if we're going to evaluate it, it will give you 0 over 0 form, which is indeterminate. And during the midterms, we already had this indeterminate forms, and you have learned already some of the methods for you to evaluate indeterminate forms. However, you may make use of the factoring technique, which now give you a value of -4 as the limit. But then f of -3 remains to be undefined. Remember, class, that when the denominator is 0, then that immediately means that the value of the function at that given x is undefined. Okay, so it is seen also on the graph that the graph, there is an open hole here. Ibig sabihin yan is excluded on that portion. Next, we have the graph of f of x is equal to 1 over x. And when x is equal to 0, we know that 1 over 0 is undefined. Okay, now if you check the limit from the left and right, as x approaches 0, y keeps on increasing infinitely as x approaches 0 from the right. However, y decreases infinitely as x approaches 0 from its left. Okay, that also tells us that f of 0 is undefined and the limit does not exist as x approaches 0. Now we wrap them all, and how do we define continuity at a point? Now you have to understand the three conditions, and when one of them is not true, then the function is discontinuous at the given x. A function f is said to be continuous to x equals c if the following conditions are all satisfied. First, f is defined at x that is equal to c. Don't be confused, because this c here just indicate a number, no, in the real number line, horizontal real number line. Okay, and the term defined means there is a real value if we're going to substitute c to the given function. And when you're solving for the limit of the function as x approaches c, then it must provide you, okay, a real value. Union term natin sa exists. And on the third condition, f of c, the first condition, should be equal to the second condition, that the limit exists. So if the limit does not exist, then you already violated the conditions. Otherwise, you may now say that the function f is discontinuous at x that is equal to c. Again, you have to recall that in the two-sided limits, you have to check the left and the right. They must be equal and they both exist for us to say and conclude that the two-sided limits exist. Okay, going back to the previous examples, let's now take a look into, let's check the continuity of this function at a given x. First, f of x is equal to x squared plus 2x minus 3 over x plus 3 at x that is equal to negative 3. So we have the first condition, f of negative 3 should be defined, no? However, if x is negative 3, it gives you indeterminate, tells us f is undefined at x that is equal to negative 3. Now, using the rule of limit, check the left and right of negative 3. However, we may make use of the factoring technique to eliminate the indeterminate form. So we can now eliminate x plus 3 and x plus 3 here. X minus 1 is left. Substitute x that is equal to negative 3 will now give us negative 4 as the limit. So the limit exists, however, the value of the function at x equals negative 3 is undefined. They're not equal. Hence, we can say that f is discontinuous at x that is equal to negative 3. So what if we are going to have another value of x? Let's say x is equal to 2. Is the function f continuous at x that is equal to 2? Now, the very first thing that you will do is to check if is 2 part of the domain of function f. We know that the domain of function f only, no, on all the set of real numbers, you just need to exclude negative 3. Meaning to say, 2 is included, making it true that f of 2 is existing or defined. F of 2 is defined, and the limit as of the function as x approaches 2 is it exists also. So they're actually the same. Okay, so the limit of the function is continuous, or the function f is continuous at x that is equal to 2. Now in number 2, at x that is equal to 0, we can see immediately on the first condition palang, it's already undefined. Then, as I've told you, when one of the conditions is not satisfied, then you can immediately say that the function is discontinuous at x that is equal to the given value of x. You don't necessarily need to check all the conditions, for as long as one of them is not true, then discontinuity is true. Now let's have other examples. If you observe number 3 example here, f of x is equal to 1 minus x squared, and you can see here, this is a quadratic function and a polynomial function. And we know that the domain of all polynomial functions is the set of all real numbers, meaning to say they are continuous for whatever is the x value. When you check x that is equal to 1 by substituting it, f of 1 is 0. And the limit of that function f as x approaches 1, whether you check it from the left and right, will also give you 0. 0 is equal to 0, meaning to say f is continuous at x that is equal to 1. Again, ano man ang gamitin mong value of x ito ay lagi continuity is true for the given polynomial function, specifically quadratic function. In number 4, we know that x minus 1 will become 0 when x is 0. When x is 1, I mean. X minus 1 becomes 0 when x is 1. But this is x that is equal to 0. So, ibig sabihin, kasama yung 0 sa domain of the given function g. Then you can say also that all conditions will be satisfied. The first condition, g of 0 is 0 because the numerator becomes 0. And the limit also gives you 0. Easy limit lang siya. Hindi siya napapabilang sa indeterminate, infinite, and others. And comparing first and second, 0 is equal to 0. Hence, we can say that the function g is continuous at x that is equal to 0. Now, what if you are asked to check if it is continuous at x that is equal to 1? You can immediately say that it is not continuous on that x equals to 1. Why? Because you can check the denominator there. Denominator check, this becomes 0 when x is equal to 1. So the first condition is already not satisfied. Okay, number 5 is the radical function. H of x is equal to the square root of x minus 4 at x that is equal to 13. Substituting 13 to x will give you square root of 9, and that gives you 3. No, they both have the same value for the evaluating of function h of 13 in the limit process. Hence, we can say that the continuity is true at x that is equal to 13. In number 6, this is the greatest integer function at x that is equal to 2. P of 2, as the process tells you, 2 minus 1 gives you 1, and the greatest integer of 1 is itself, because 1 is integer already. Meaning to say P is defined at x that is equal to 2. Now checking the one-sided limits for us to determine if the two-sided limits or the limit of the greatest integer x minus 1 as x approaches 2 does not exist, we need to check the left and right. Now if we check the left of 2, so we can have 1.999, almost 2 but not equal to 2. We can check right of 2, we can have 2.0001, okay, as a sample value. And when we are going to follow now the rule, the greatest integer of 1.999 minus 1, now this gives us a 0.9999, meaning to say the greatest integer of this is 0. Now for right of 2, okay, 2.0001 subtract 1 will give us 1.001, and the greatest integer of this is the whole part 1. So 0 is not equal to 1, meaning to say the two-sided limit does not exist. And since we were not able to satisfy the second condition, then P is discontinuous at x that is equal to 2. What if let's have another number aside from 2? Let's say at x that is equal to 0.5. So let's check the first condition. First condition, P of 1/2 or 0.5, the greatest integer of 0.5 minus 1, and this is equal to negative 0.5. And the greatest integer of negative 0.5 is negative 1. Now, if you check the real number line, this is 0, this is negative 1. So the integer on the left of negative 0.5 is negative 1. Now, if we're going to check the two-sided limit, if we are going to first check the right limit of the greatest integer of x minus 1, as x approaches right of 0.5, the greatest integer of x minus 1 as x approaches left of 0.5. Now we can assign numbers to this. Let's say right of 0.5, let's have 0.5001, almost close, very close to the number. Left of 0.5, we can have 0.4999. Let's have the substitution. We're doing this just to check if what happens to the limit if we are definitely getting the value very close to 0.5 from either side. Okay, so we have here substitute. Okay, minus 1. So what about this? 0.4999 minus 1. Okay, sa taas, makikita natin that this can be 0.4999. And yung nasa isa naman, this is negative. This must be negative 0.4999. This and this is negative 0.5001. And if we're going to check now, get the greatest integer of these two, they are providing the same value. They are providing the same value, and that value is negative 1. And since negative 1 and -1 are both derived from the left and right, then we can say that the limit in the two-sided limit of the greatest integer of x minus 1 as x approaches 1/2 in the two-sided is equal to -1. So it exists. Now, if we are going to compare the first and the second condition, we can now say that on the third condition, since in the evaluating function, it provides us -1. And in the limit process, -1 also was no, calculated as the limit, then all conditions are satisfied. Then we can say that the limit, the function p is continuous. The function p is continuous at the given x that is equal to 0.5. Okay, let's have the next, the piecewise function. On the piecewise function, you have to be very conscious on the domain, the subdomain of each subfunction. Okay, we're going to prove if function m is continuous at x that is equal to 2. Now we can do the evaluating of function m of 2. 2 is here, so we can have x minus 1 as a function. Substitute, let x be equal to 2, so we have 2 minus 1 is 1. So m is defined at x that is equal to 2. Now we're going to check the one-sided limits. We check right and we check left. Checking the right, so right means the set of numbers greater than 2. So we can have this, the third subfunction. So let's use the constant function. Limit of 6 as x approaches 2 from the right is 6 because that's constant. Now if we check the left, then we are going to use x minus 1, the linear function. So the limit of x minus 1 as x approaches 2 from the left is 2 minus 1, and that's 1. Now we can observe that 6 is not equal to 1, meaning to say the limit does not exist for the function m as x approaches 2. Hence, we can say that m is discontinuous at x that is equal to 2. Okay, in number 8, this is the cosine function, and we know that the domain of cosine is a set of all real numbers. So, ano man ang gamitin nating input na laging totoo yung tatlong conditions. Okay? T of pi, cosine pi is -1. Limit of x as x approaches pi is also -1. That's basic substitution. And definitely -1 and -1 are the same. Then all conditions are satisfied. Then t is continuous at x that is equal to pi. Again, whatever is your input, or whatever is that point, then cosine is always continuous to that point. Number 9, the natural logarithmic function ln of x at x is equal to e. Check the first condition. B of e is ln of e, and that's 1. So b is defined at x that is equal to e. On the second condition, limit of ln of x equals, as x approaches e is equal to 1. That's basic substitution because ln of e is simply 1. 1 and 1, both the same. So the third condition is also satisfied. Hence, we can say that b is continuous at x that is equal to e. The 10th example is the exponential function r. R of x is equal to 3 raised to x minus 1 at x that is equal to 3. Then we can say here that on the first condition, r of 3 will now give us 9 because we just need to substitute x that is equal to 3. So 3 raised to is 9. So r is defined at x that is equal to 3. On the second condition, get the limit, then that's just a basic limit process, that gives us 9 also by substituting x that is equal to 3. Now the third condition, compare them. So 9 is equal to 9. Hence, we can say that r is continuous at x is equal to 3. Take note also that exponential function accepts any input. Okay? Ang domain niya is a set of all real numbers. So ibig sabihin, ano man ang gusto mong i-test sa continuity, laging mapapatunayan na yan ay continuous to any element, to any point. And yeah, This is an example to that of continuity, the bridge that you can see at Cabagan and Santa Maria, wherein the bridge now connects the gap between the two municipalities. Okay, and that's about continuity. The bridge becomes a tool or a mean to have, you know, to have a sustainable, development here in Isabel. So that's all about the continuity. Let's on the next video, let's talk about continuity at or other types and the continuity on an interval.